Hello, I'm Roman, and welcome back to the series of the videos Neural Networks from Scratch in Golang, where we're using this book called Neural Networks from Scratch in Python, but we writing everything with the Golang, right? And in the previous video, I kind of finished. Well, I made the main thing I was mostly concerned about, and that is this we like using this optimization for category cross entropy loss. Where's it? Okay, so the one I finally found a way to inject. So instead of putting it inside the train code, I put it, well, I created a separate classes that will share the implementation. I mean, it looks like this. So we have the another version of the softmax activation, which uses the softmax activation under the hood for all of the forward pass stuff. But for everything, well, for the backward method, we actually do not implement it. And for the inputs, we return this combined the inputs calculation. For the loss, the same. It uses the actual categorical entropy loss under the hood for all of the forward paths, but for the backward path, it actually calls this optimized implementation. And I have the factory method that creates both objects, and we have this backward implementation. So there is one thing, but once I try to create the category prediction model that we had before, uh, I faced an issue. So if you take a look, you can see that there is a incorrect dimension for the categorical accuracy calculation. And it actually, once I dive into the problem, it actually made sense. It's categorical in the accuracy. So here I wrote it in a way, by the way, in correct. I actually wrote it in a way that it assumes that the predictions and the target has the same size. And the thing is that it actually only suits for binary regression, but not for, but it's not suitable for prediction of the categories. And I still don't understand why they wrote this accuracy here in this way. Not sure. I will try to find it. Accuracy. Okay, this one. So I'm not sure why it's written in this way. For me, it's actually, I need to do the opposite because I have the list of the predictions, which basically list of the numbers, and inside y in the target, I have kind of one-dimensional array with the numbers, well, with the values that represents actual category that we're going to use. And I mean, I've been thinking why I kind of need to put it inside one, right? And what I'm thinking, I will just create two versions of the categorical accuracy. The first one will be for the binary, and that's basically what I have here. And the second one will be for the categorical, for the categories, well, actually for the predicting of the classes, and I will implement this logic inside it. And so then we can use, the first one is for the binary, and the second one is for the actual predictions of the categories. It should work, and that will be my task for today. I will call it binary categorical accuracy, and I'll do it the same. Then I have this binary categorical, right? And yeah, so then I'm going to create the next one, and that should be just categorical actually, right? We'll post it here. So, okay, actually I had to copy this one, but okay. Mm, So I don't need to do this, but no, I probably will need this. So I have two things. First, I need to go to the binary model, and that should be binary categorical accuracy. Then I'm going to not regression categorical model, and okay, this one, that's the one I want to implement. I do not check the dimensions for the predictions and the target because I do not expect that they will be the same, but the result should be by the number of the rows, but this one will be actually not by the number of the calls, at just one value. And we will ignore it. And what it means, I'm not going to the range. Oh no, actually I need calls. I need calls here. So this 0 j less than calls j plus plus, right? And then I need to do some stuff, and I need to, so that's so what's the idea? I need to take, well, I need to calculate the maximum arc index, something like this. I mean, I've done it before, but I'm not sure. No, this one. Max. Max index. Yeah, this one. Okay, so this is what I need to do, right? Something like this. I actually don't need the loop, I think. What I need to do, I take the raw values from the predictions, then I calculate the max index, right? And the results of the comparison will be actually, I'm taking the maximum index, which will be, okay, for the transparency, it's actually predicted class, predicted, okay, predicted value. Let's call it like this. And I have the predicted value, and it should be equal to target value at I0, right? And that's it, basically. Right, so I take the row view, which means that I'm taking all of the predictions for one sample, where each column returns the probability of the concrete class. Then I convert it into the class value, starting from 0, 1, 2. And I think I have the same for which one I'm using. Which data sets? I mean, what data set I'm using? Mhm. Spiral data. Spiral data. Yes, it returns from 0. So that should be it. Now I need to on this one categorical and run categorical model. Okay, so it should work. Zero length in matrix dimension. Model go. Wait, categorical model go model 94. Model um zero length in matrix dimension. Okay. So it looks like my optimization didn't work. It means that it's time for debugging, right? Let's take a look. Um, okay. Do we have something here? No, it's actually 0. Okay. Implementation. Mhm. Maybe the problem with the devalues? No. No. So we have some stuff going on. And mhm. Okay. Return nil. And that goes inside loss, which is okay because then it passed into the activation backwards. That's fine. Then we go into layers get inputs and it falls inside this one, right? And there's 0. Okay, so okay. So there is a problem of how I access the data, right? Mm, Debug package. Beautiful. Okay, we have a backwards. Can I check the address? how I can check that they unable to evaluate expression, couldn't find symbol. Call a backwards in. Okay, call L backwards implementation. No, okay. So they're the same, right? And then maybe the problem is how I store it. No, I mean the inputs should be fine. I'm just curious what will happen. Right. Why? Hmm. So you want to tell me that this approach, okay, I need to read about this stuff. I think, oh, I mean about the Go one. So you want to tell me that that's actually returns something? No, okay. Actually returns something. Okay. So I mean, we have the regularization loss, we have the accuracy. It's actually run pretty fast. Works slowly, but I remember that this amount of the nodes and the amount of the data already was kind of slow, and yeah, on the second epoch it kind of gets the high accuracy, and yeah, I think I have very good accuracy, which maybe actually. Oh, I think that's because we increased this randomization, what's called, uh, factor on the dense. Because if we take a look at dense at the layer class, there is a what's called initialization, and I think yeah, this is the one. So that was like this. So it should start worse. Yeah. Yeah, but it still jumps pretty quickly on the accuracy. But I think this is more like here. Yeah. Probably I will need to wait, but it seems like everything's working as intended. Now we have got this model class. We're able to define new models without writing a large amount of the code repeatedly. Writing code is annoying and leaves more room to make small, hard, noticeable mistakes. That's true. Ideally, if you want to do some refactoring or rewriting of the code, you should, and I should cover all of the things with the test, and probably I will explore. I just not sure if it's needed to explore this in this series, but the interesting question is how to cover all of the things with the tests and how's it called? Cover all of the things with the tests and actually have all of the parts testable. The only thing is I will need to mock the randomization part somehow, so we'll always have the same testing data, the unit test, so we can actually run the test and be sure that it works as expected. But how long? 22 minutes, just 22 minutes of the recording. Okay. So full code at this moment. It's actually pretty big. Yeah. And this is all implemented. Okay. And what do we have here? Sample code. Okay. So it's actually will be easier to copy paste it. So I will go for the next one, right? That probably will be code that is far away from. It's very interesting. This code is OpenCV. I mean, I like OpenCV, but then there is a question how to. I mean, there are ways to integrate this into the Go, so that's what I will be exploring. But looks like I will start this chapter a little bit, and probably that's it. Because the main thing I wanted to finish with this, with the model class, which I actually did. Okay, so let's take a look what we'll be dealing with next. In practice, deep learning tends to involve massive datasets, often terabytes or more in size, and the models can take days, weeks, or even months to train. This is why so far we have used programmatically generated dataset to keep things manageable and fast, while we learn the math and other aspects of the deep learning. The main objective of this book is to teach how neural network works rather than the application of the deep learning to various problems. That's true. That said, we'll explore a more realistic dataset now, since this will present new challenges to deep learning that we have not yet to consider. If you have explored deep learnings before reading this book, you have likely become acquainted and possibly annoyed with the NIST dataset, which is the dataset of the images of handwritten digits at the resolution of 24 by 20, 28 by 28 pixels. It's a relatively small dataset and is reasonably easy for models to learn. This dataset became the hello world of the deep learning, and it was one of the benchmarks of machine learning algorithms. The problem with this dataset is that it's comically easy to get 99 plus percent accuracy on the NIST dataset, and doesn't provide much room for learning how various parameters impact learning. In 2017, however, a company called Zalando released a dataset called Fashionist, which is a drop-in replacement for the regular MNIST. Fashion is an old image dataset for benchmarking. The Fashion MNIST dataset is a collection of 60K training samples. Still training? Okay. Of 28 by 28 images of 10 various clothing items like shoes, boots, shirts, bags, and more. We'll see some examples shortly, but first we need the actual data. Since the original dataset consists of binary files containing encoded in a specific format image data for this book, we have prepared and are hosting a pre-processed dataset consisting of the PNG images instead. It's usually wise to use lossless compression for images since lossy compression like the JPEG affects image by changing their data. These images are also grouped by labels and separated into training and testing groups. The samples are the images of articles of clothing and the labels are the classification. Here are the numeric labels and their respective descriptions. Okay, so it starts from 0. Okay. Because, for example, in my codes, the way I implemented the calculation of the accuracy, it always has to start from the 0 label because that's how the indexing for the arrays are working. Data preparation. First, we'll retrieve the data from the neural networks from scratch.io site. Let's define the URL of the database, a file name to save it locally, and the folder for the extracted images. Next, download the compressed data if the file is absent under the given path using the URL lib standard Python library. But can just do it once. Well, no, I wouldn't do it once. I mean, I can do once it with the wget library and just then unzip it and write something in the bash. But I think for me it will be a good practice to write something, something like this with the Golang, and I will write some zip file downloader for this one. You should and the next, yeah. You should have a directory called fashion mist images containing test and training directories and the data licensing. Inside of the both test and train directories, we have 10 subcategories, number 0 through 9. These numbers are classifications that correspond to the image within. For example, if you open the directory 0, we can see these are images of short with either short sleeves or no sleeves at all, for example. Okay. It's common practice to grayscale, go from 3-channel RGB values per pixel to a single black. Yeah. I mean, yep. There is a high chance that the next thing after this series I will go rather into implementation of the rendering engine or into convolutional neural networks because I mean I like to work with the images and yeah. Through the theme methodology, grayscale is also a common practice to resize images to normalize their dimension, but once again, the fashion is that says prepared. Yeah, it's already squared, and usually the square image is very good for the models. Yeah, I actually have pretty good accuracy, 88%. I do well. It's definitely overfitting against the training set looks like the model is too big for this data set. So, but yeah, I mean, the cool thing is it actually, I mean, it's done, right? And I will comment, actually, do I have the to do? Actually, I think check out the, yeah, so what I'm doing, I don't need this anymore. So let me check again. I don't need to write anything. I will stop for today because the next series will be, I think, messing around with some Go code to download and zip stuff. Looking on the images, I will need to. I know that there are some bindings for the OpenCV for the Go. I just need to, set up it, edit the dependency, take a look at the API if it's too different from the OpenCV API itself. And yeah, that will be the case for the next series, which I will record tomorrow. Thank you for watching, and I see you tomorrow. Bye bye.